3, and as previously what we were discussing, and I might have told you that now we will be taking up a very important, very systematic part of the integration known as definite integrals, where we will be repeating all those which we have done, namely integration through standard forms, we will be doing integration by substitution, we will be doing integration by parts, and a few questions integration by partial fractions. The only thing is that I'll advise you to recall the time when I told you a little definition of the definite integrals, where I talked about the area through definite integrals. We have talked about the limits, the lower limit and the upper limit, and then we have told that there is no constant of integration for the definite integrals. We take up examples, we take up definitions, and we take up formulae wherever and whenever required. So, we now proceed basically with the first definition, that is kind of a repetition that we have done sometimes in the previous lecture. We take up those concepts and those problems. We have this topic called as definite integrals, and I start the first that we have done earlier. You can call it briefly as definition without going much into details of mathematics. This is written as a to b fx dx is equal to some integral that we used to have even before, a to b. This is called as lower limit, this is called as upper limit, and finally this is written as, in place of x I write upper, with a negative sign I write the lower limit, and that is all. There is no constant of integration, so I write here we do not have any constant of integration, and the value of this one fb minus times fa is always constant. It could be negative or positive or maybe 0, but then the area cannot be defined. So, usually we do not get 0 here, but negative and positive values are always possible. So, this is the basic fundamental, and what we will be doing again by standard forms, we will be doing by substitution, and then we will be taking a parts. So, I will be calling it, to make more easy this part of integration, let me call it section 1 here. Definite integrals for standard forms and substitution. I'll take together and substitution. Definite integrals for standard forms and substitution. What we do is, for standard forms we will write in the same way. Let me take couple of examples for you. Only on standard forms, substitution will make it more easier for you to understand, but let me take one exercise. This is what we call as 1. More, as I have told you, I will be taking along with the substitution. This is just elementary. If I want to make it from 1 to 2, lower limit is 1, upper limit is 2, I am to integrate 2 minus 3x plus x square minus x cube dx. If you look here, the basic, all the rules and all the formula remains the same, term by term integration. 2 outside, this will be 1 to 2 dx minus 3 outside, 1 to 2 x dx. Formula remains the same, only thing the difference is this, plus this will be integral x square dx ranging from 1 to 2 minus ranging from 1 to 2 x cube dx. I can integrate, which you know. So, integral becomes x for this, the limit is 1 to 2, 2 outside, minus 3. This will be x square upon 2, the integral from 1 to 2. If you look here, this 1 to 2 is similar as a to b, whether you put it in a big bracket or small bracket makes no difference, plus this will be x cube limits from 1 to 2 minus this will be x4 upon 4 1 to 3 1 to you can 1 to 2. So everything is easy. This will be 2 minus 1. Look in here, this will be 2 upper limit minus 1 in place of x, minus I can make it 3. This will be 4 upon 2 minus 1 upon 2. You could have even brought this 2 after squaring outside. This will be x cube, means 8 minus 1 minus I bring 16 outside, 4, so 32, 4 times. So you will be having x, if I put here in the value, so it will be 2 to the power of 4. That means 2 into 2, 2 into 2, 4, and this 4, it will be rather making it here, I will be making it 16 minus 1, like this, 16 minus 1. And so we will be having 2 minus this, you can make it 3 by 2 multiplied by 3. This will be 7. Here it is will be 15 by 60. Is simple as usual. So 2 to the power whole square, and this will be 2 here, and so it will be 1 to 2. So x4, I have written 2 to the power 4 from 1 to 2. You can write as such. You solve everything to a numerical value that will be constant, and that is what we learned just now in the theory of the definite integrals and through the definitions that we have. But nonetheless, another example that I would like to have is the second simple standard. So I have to evaluate integral equals to 2 to 4. This is 5 minus 2 times x power 1 by 2 plus x to the power minus 2 minus x plus 1 whole to the power minus 3 upon 2, the big bracket, that means it ends here, and dx. All standard forms similar to be done, and so that is equal to, first thing, 5 integral 2 to 4 dx minus 2 outside integral x to the power half dx plus this will be integral, this will be again 2 to 4. We will continue term by term. Integral ranging from 2 to 4, this will be x to the power minus 2 dx, and last 2 to 4, this will be x plus 1 whole to the power minus 3 by 2. We will not solve it completely because you know everywhere I'll be using the standard form x to the power n dx is equal to x to the power n plus 1 upon n plus 1. Remember, we do not add any constant. Remember that we have a constant value giving solution to each of them. We come to substitution, and with one result we will explain how do we do that. Substitution remains the same. The only thing is possibly the limits will be changing. I take up the first example like this, the first exercise. But before that, there are certain trigonometric functions that I will be having whose values are required up to 0 degrees or 30 degrees. So let me make a table. So I will call it as a table of angles of trigonometric ratios. Trigonometric ratios. I believe that you have a little idea if you have read trigonometry earlier in your previous classes. I'll put it here, angles, that is 0 degrees, 30 degree standards, 45 degrees, then we have 90, 45, and then we can have in between one thing. We can have 60 degrees, we can have 90 degrees, and we can have 180 degrees will be sufficient. If there is sine 0 is always 0, sine 30 is always half, sine 45 is root 2, sine 60 is under root 3 by 2, sine 90 is 1, and so 180 degrees, that is 0. So let me frame it in a very tabular form. Will make it more easy for you to understand. I'll be giving only the standard forms which we will be using more often. This is what we call as sine. Then I can have cos, that means cosine. We will be having cos 0, 1. Cos of 30 I'll be having under root 3 by 2, same thing here. This will be the same, that is 1 upon root 2. This will be replaced by half, and we will be having it 90. 90 we can have, that is 1, and cos 90 is 0. And so this I'll be getting as minus 1. The last one, which invariably we use, tangent of 0 is 0. Tangent of 30 means this, so it will be, I'll be getting 1 upon root of 3, and this will be 1, and this will be root of 3, this will be infinity, and this will be 0. That marks the end. There are various others. I am not taking all of them, but this is just at a glance that I can have the list of the formulae that is placed here. They are very important to remember, and those who have studied the trigonometry in the earlier chapters, we have been given these values. I take up, if sometimes it comes, we will be able to understand it. So let me take it, the first exercise, or rather I'll call it third, because 2 examples that I have already taken. I remind you, I am starting integration by substitution in case of definite integrals. Method remains the same. Basic ideas of substitution remains the same. The only thing is the definition changes. So we have integral is equal to evaluate e to the power x dx upon 1 plus e to the power x ranging from 0 to 2. If you recall, very early when we started integral calculus, I have told you that these are the values x is equal to 0 to x is equal to 2, but more often we don't write every time these. So I will be substituting 1 plus e to the power x is equal to u, which we usually do, and therefore e to the power x dx is equal to du. I know that these have the substitution even when we were doing previously. Only important thing now is this transformed or transformation formulae. That means x is transformed or replaced by u. The limits will also change, because this is the limit, as I have told you, is for x. Since everything is changing into u, I will have a new limit for u also. Look in here, I am changing from here. That is equation number 1 implies, if this is the only important thing that you will be taking care of, if we have x is equal to lower limit 0, u will become e to the power 0. Look here, e will become e to the power 0 plus 1. E to the power 0 plus 1. Anything raised to power 0 is 1. This 1, and so u is equal to 2. I hope that is clear. So this is u is equal to 2. If the upper limit, if x is equal to 2, then what happens? U is equal to 1 is there, and plus e to the power 2 will remain as e to the power 2. So u is the new limit. Limits can be anything that we can have here, and these are the tables that is to be noted, that is to be remembered, and that is to be taken care when we are using trigonometric functions as limits. So now the new limits becomes like this. Therefore 1 implies, with all these integrals, I'll be having integral is equal to, the new limits is u is equal to, when I have put 0, it gave me u is equal to 2 to 1 plus e square. The new thing, e to the power x dx, that becomes du. This was u, 1 plus e to the power x. The method remains the same, and I'll be having it log of u. As I have told you, by definition, this will vary from 2 to 1 plus e square. Put these values. Log of 1 plus e square minus log of 2. No constant of integration. And one more difference between indefinite integrals and definite integrals, you may notice here that in indefinite integrals, after substitution, we used to return back to the original variable by putting the value of u, v or theta, what we have substituted for. But here we don't do so, and straightway come to the constant value. That is the only difference that we have. The first difference is that we don't write capital C, the constant of integration, and second, that we need not to, that there is no need to return back to the original variable, because the moment we substitute these new limits here, they are the limits of u. Previously it was of x, and the same definition follows, and the answers will be given. The next exercise that I take is fourth exercise, and this is integral is equal to 0 to 1 3x dx upon 1 plus x square. Again substitution comes, x square has a difference 2x, so I'll be writing it. Put 1 plus x square is equal to t. So naturally I'll get 2x dx is equal to dt. So obviously I only need x dx is equal to dt. This is all known to us, we have done many times. From here I'll be doing that change of limits. If x is equal to 0, I can now write directly t will be equal to 0. If x is equal to 0, this goes off, t will be equal to 1. If this you will have to write on the fair answer, on the fair page of your answer where you are solving, to show that the new limits for t are as under. If x is equal to 1, if I put x is equal to 1, obviously t will be becoming 2, new limits, and hence the integral now with the new limits becomes x0 will be t1 to t2, and I'll be having 3 outside, I'll be having 2 from here. This will be dt upon t. I hope there is no confusion now. X dx is replaced by dt upon 2. This 3 outside is because of this 3. Everything is okay. This is the representation of t. So it will be t varying from 1 to 2. And so here, look, I will be writing it. Integral is equal to, I am writing here, is 3 upon 2. We know the value. It will be log of t, standard, varying from 1 to 2. No constant of integration. The definition is first in place of t, I will be putting the upper limit. In place of t, I will be putting the lower limit. And so this will be 3 by 2. Inside, this will be log of 2 minus log of 1. But very incidentally, this log of 1, if I recall, I have told you earlier, this log of 1 is always equal to 0. And we have the answer, I is equal to 3 upon 2 log of 2 only. That's all. That is how we have seen. The only difference is in substitution, in case of indefinite integrals, we change the variable from x to y, or from x to theta, or from x to u. But in case of definite integrals, we do the same thing, but we do not return back to the original or the initial variable. Instead of that, we put the new limits, get the constant answer, which is according to definition justifies. Now we take up this question, that will be 5th. We are to evaluate the integral 0 to, I'll give you an idea of this, radians pi by 4. This is sine square 2x upon 1 plus cos of 2x dx. Let me call it 1. 45 degrees is equal to, in radians, is called as pi by 4, where pi is 180 degrees. Is much known, and there is no problem in understanding this. So this is pi by 4 is nothing by 45 degrees. Similarly, 60 degrees, if there is any, I can write it pi by 3. So 3 c's are 680 and pi remains 180 degrees. Since I am not using this, let me erase. I am using only 45 degrees, that is pi by 4. The solution begins like this. There is a little trick that we apply here, which we used to do even in case of substitution. Pi by 4. The sine square x is written as, I am using this formula, that sine square 2x plus cos square 2x is equal to 1. We have done number of times in all previous lecture that you can refer to. So I'll be having it in place of this 1 minus cos square 2x upon 1 plus cos of 2x dx. No confusion. Sine square is written as 1 minus. So the integral now becomes 0 to pi by 4. This is a minus b, a plus b. So I'll be writing 1 minus cos 2x into 1 plus cos 2x upon 1 plus cos 2x, reduces to a very, very simple form. This 1 plus cos 2x cancels with this, and I get a very simple integration. There is no need to substitute even at this point of solution. I'll be getting only, which I did in the first 2 exercises. This will be taken as 0 to pi by 4. This is 1 minus cos of 2x dx. I'll integrate. I'll have it 0, the original limit, dx minus integral 0 to pi by 4 cos of 2x dx. Standard forms. We have not done any kind of substitution here. So I'll be having it x, this x, 0 to pi by 4 minus, integrate this, it will give you 1 upon 2 sine of 2 times x, 0 pi by 4. I will advise you to refer to the table which just now we have seen. This will give me pi by 4 minus 0. Definition, upper limit minus lower limit, minus 1 by 2. Look in here, I will be having sine, in place of x I will be putting pi by 4, this 2 will cancel and will give me pi by 2 minus, this will be sine of 0. 0 means 0 degrees. I have put the limits referring to standard values. This will be pi by 4, 0 we are not mentioning, minus 1 upon 2. I will be having here sine pi by 2 means 90. This pi by 2 is written as 180 degrees pi upon 2. So this is obviously 90 degrees. Sine 90 is 1, sine 0 is 0 according to the table. So this will be pi by 4 minus 1 by 2. Once again, there is no constant of integration. The answer I is equal to, more so precisely, I can take 1 upon 4 out. So this will be pi minus 2 to the maximum that we can do. But the first answer was okay. We take up the sixth exercise now. This is a very important question, very good question, as we can see, giving a new formula for it. We come now to something where we call it, this is the substitution. We have seen that in substitution we have change of variable, and in that change of variable limits also changes. Then we come to next, that is what we call as, this I can call as section 2, definite integrals for integration by parts, definite integrals for integration by parts. But before we take up any question, I'll show you that formula is like this. Formula remains the same, a to b product of two function fx into gx. dx, which we used to write, if you recall, a to b u into v dx. We write it as first function into integral of second v dx, whole of this limit a to b, minus, this is a to b differential of first du upon dx, integral of v dx, and whatever the integration now will come, we will put the limit. Remember, we don't put any limit here, we don't put limit here, the whole is limited, and therefore this I enclose, call it a very important formula. This formula we have done, of course, but now for the integration of definite integral, we must know where to put the limits and where we do not put. Remember, here we do not put, here we do not put. In the next lecture, we propose to take up few more examples on substitution, and mainly we will proceed further by applications of this integration by parts, which will make it more easy for you to understand how we use this formula. Thank you for your attention for this lecture.